Let's continue ZEUS training section 4, Linearized Euler solver for rapid frequency domain aeroelastic analysis. So first we'll go over the motivations here. Traditionally, the aerospace industry has relied heavily on the linear panel codes such as the doublet lattice method and ZEUS for routine aeroelastic analysis. In this instance, only a surface panel model is required and no tedious mesh generation is involved. And the aerodynamic influence coefficient matrix, called the AIC matrix, generated by the linear panel codes, is independent of the structural characteristics and be computed once and then saved for further analysis. Now, with the advance of computer technologies, routine aeroelastic analysis using CFD codes is now becoming affordable. And the time domain simulation by CFD, coupled with a structural solver, can generate a nonlinear aeroelastic response. However, this is too expensive for routine industrial applications because the time domain simulation is required at each flight condition, which is Mach number, altitude, and angle of attack, where altitude, of course, represents the dynamic pressure. Now, only information of the lowest flutter mode is obtainable, and the next flutter mode cannot be reached by the time domain simulation because the response is dominated by the first flutter mode, and you won't be able to see any further flutter modes. Now, the frequency domain unsteady aerodynamic generation using CFD is desirable because all of the downstream frequency domain aeroelastic modules, such as Flutter, dynamic loads, and ASC, remain unchanged. And the PK and G methods can search for all of the flutter modes, not just the first flutter mode. So let's review the frequency domain generalized aerodynamic forces. In general, the frequency domain equations of motion of an aeroelastic system excited by control surface deflections and atmospheric gust can be expressed in this equation, where our aerodynamic matrices are QHH, QHC, and QHG. The QHH here on the left-hand side is the generalized aerodynamic forces due to the structural modes. QHC is the gaps due to control surface deflection, and QHG is the gaps due to gust. These three gaps represent the linearized frequency domain unsteady aerodynamics about a nonlinear mean flow condition due to a small perturbation of structural deformation, control surface deflection, and gust excitation. And CFD codes must be capable of generating these three gaps if you want to do frequency domain aeroelastic analysis. And of course, we're going to see how ZEUS can generate these three gaps for the analysis. So first we'll look at the formulation of the linearized Euler equation. Now, the full Euler equation we've seen before is a conservative differential form and in curvilinear coordinates is given by this equation, where Q is the vector of conservative fluid variables, H1, H2, and H3 are the convective fluxes in the three curvilinear coordinate directions. Now, assuming the structural oscillating amplitude to be very small, the total unsteady flow can be decomposed into a steady part and an unsteady small perturbation part. So Q is now Q bar plus Q tilde, and Q bar is the steady part, Q tilde is the unsteady part. And then similarly, we break up H1, H2, and H3 into steady and unsteady parts. Now this results in two equations, the steady Euler equation and the linearized Euler equation. And this equation here is the linearized Euler equation. Now, applying the Fourier transform yields the frequency domain linearized Euler equation shown here. So now, instead of our functions being a function of t, we're now a function of I omega. Now, A bar c, A bar eta, and A bar sigma are the mean flow convective flux Jacobians called the steady background flow and can be provided by the steady Euler solution, which is only required to compute once. And then a pseudo time matching scheme to solve the linearized Euler equation that has the steady Euler solver's computational efficiency is the result. Next, we'll look at the linearized unsteady transpiration boundary condition. The full Euler boundary condition on the lifting surface is given here in this equation, where U, V, and W are the flow velocity components, and F consists of the thickness of the body and the unsteady motion of the body. Now, once again, we assume that U, V, W, and F can be split into steady and unsteady parts. So this yields the steady and the unsteady boundary condition in the frequency domain given here. Now the unsteady boundary condition is applied on the stationary grid. So by doing that, no moving mesh is required, and this is consistent with the assumption of small perturbation. But however, we saw earlier in previous sections that even amplitudes up to 15 degrees can be reasonably approximated by this small perturbation assumption. Now F tilde of I omega can be structural mode shapes or control surface mode shapes, which leads to the generation of QHH and QHC. So next we'll look at the gust. The QHG of I omega is the gaps due to the traveling Dirac delta function as shown in this figure. So this delta of T minus x naught over V is the traveling Dirac delta function, where x naught is the reference point of the gust and x is a point on the aircraft. Now the frequency domain counterpoint of the traveling Dirac delta function can be obtained by the Fourier transform as shown here. So we just have e to the I omega times x minus x naught over V, where delta bar of I omega is the sinusoidal gust. Now the induced angle of attack due to the sinusoidal gust is given by alpha of I omega equals delta bar of I omega over V. And the linearized unsteady transpiration boundary condition for the sinusoidal gust is now given by this equation here, where our gust term shows up right here. So we'll look at some validation here. This is the unsteady CP on the LANN wing at Mach 0.822 and a reduced frequency of 0.102 with the pitching mode. Now the linearized Euler solution is validated with the full Euler solution at 4 span stations. We're looking at 20%, 47.5%, 65%, and 82.5% of the span. We have 2 pitching amplitudes, a quarter of a degree and then 0.05 degrees. And these are used to generate the full Euler solutions. Now in the linearized Euler solution, the pitching amplitude is not involved because it's an exact amplitude linearization method. And now with the full Euler solution, we'll see as the pitching amplitude becomes smaller from 0.25 degrees to 0.05 degrees, the full Euler solution approaches the linearized Euler solution. And the LANN case demonstrates that the accuracy of the full Euler solution is amplitude dependent. So our red dashed line is the linearized Euler ZEUS solution. The blue line is the ZEUS 0.25 degree full Euler solution, and then the green line is the full Euler solution with a pitching amplitude of 0.05 degrees. So here we have the real and imaginary components at 20% span, real and imaginary for 65% span, real and imaginary for 47.5% span, and then real and imaginary for 82.5% span. Looking at this plot in particular, you can see that the full Euler solution peak is right here for the 0.25 degrees, and then as we go up to 0.05 degrees, it gets larger and it's closer to the linearized Euler solution. We can also see that in the 47.5% span case as well. So as we said, as you decrease the pitching amplitude in the full Euler solver, it approaches the linearized Euler solver solution. Next, we'll look at the validation of QHC on a Saab Canard-Wing configuration. The Saab Canard-Wing configuration consists of a canard and a wing with a gap of 0.1 inches in the vertical direction between them, as shown in this figure here. Both the canard and the wing are modeled as flat plates at an angle of attack of 0 degrees. And the canard pitches about its 50% root chord, and the wing remains stationary. Now the lift on the wing is induced mainly by the downwash or the wake from the pitching canard. And because the pitching amplitude of the canard is assumed to be infinitesimal, The unsteady flow becomes completely linear, for which the potential equation and the linearized Euler equation become nearly equivalent in the Mach number range considered. Now to model this in ZEUS, we have two blocks of mesh. The first block contains the wing, and it's the global block, and then the second block is just the canard, and that is embedded inside the main block. Now the ZEUS solutions of lift on the wing versus reduced frequency due to canard pitching oscillation agree with the ZEUS solution very well. The ZEUS solution is shown by the green boxes and the green line, and the ZEUS solution is shown by the black circles. And you can see here for Mach 0.8, our real and imaginary agree very well. And then we've also done Mach 1.054. It's not 1054. And that also agrees very well. And then next we'll look at the gust gaffs of the Goland wing. The Goland wing has a 4% T/C airfoil section, and at Mach 0.7 the flow is nearly linear, so that the ZEUS potential solution is valid. So we'll compare once again the ZEUS results to ZEUS. And we see good agreement between ZEUS and the linearized Euler solution, which validates the gust gaff of the linearized Euler solver. So ZEUS is the solid lines, and ZEUS is the open symbols. The real part is red, and the imaginary part is blue. So you can see mode 1 as a function of reduced frequency from 0 to 1. We've got very good agreement. And then for mode 2, also we have very good agreement between ZEUS and ZEUS. So next we'll do a frequency domain Flutter analysis on the AGARD 445.6 wing. The Flutter solution is computed by the G method using QHH at 5 reduced frequencies, and the linearized Euler solver in this case is about 7 times faster than the full Euler solver. So the Flutter speed is on the left, the Flutter frequency is on the right. Our experimental results is the red circle and line. The ZEUS linearized solver is the blue, the solid blue triangles. The full Euler ZEUS solution is the open blue triangles, and then ZEUS is the green boxes. So you can see that our ZEUS matches both the Flutter speed and the Flutter frequency quite well with the experimental results. Furthermore, we can see that the linearized ZEUS solver and the full Euler ZEUS solver are pretty close together. However, the linearized Euler, as we said, is much faster. So what are the merits of the linearized Euler solver? It is an exact amplitude linearization method, which is more efficient and accurate than the full Euler solver, and the gaffs due to structure modes, control surface kinematic modes, and the sinusoidal gust can be generated by the linearized Euler solver, which allows for a wide range of aeroelastic applications, including flutter analysis, aeroservoelastic analysis, and gust analysis. Next, if the steady flow solution is generated by a viscous computation, then the linearized Euler solver can provide accurate, unsteady shock structure in the small amplitude sense. And this is because the unsteady shock location is dominated by the steady shock location, and the boundary layer method of ZEUS can provide an accurate viscous solution. And no boundary layer coupling is required for the unsteady computation, which greatly simplifies the computational scheme for solving the linearized Euler equation. Finally, the linearized Euler solver at 0 reduced frequency can be used to compute the aerodynamic stability derivatives. And the steady aerodynamic stability derivatives, for example, CL alpha, CM alpha, etc., require only the real part, and the damping stability derivatives, CL alpha dot, CM alpha dot, etc., need only the small reduced frequency.